Okay, for our second example, we're going to look at that lifeboat and life vest problem from yesterday. So this was exercise 2A, and Lissa mentioned that all of you were sort of beguiled by what the objective function was, and it was a little subtle because it was, usually it's at the end of the problem that they ask you to maximize or minimize something, but this one initially said that the ship's captain wanted to maximize number of lifeboats because they're more comfortable for people. So that's going to be our objective function, is essentially just to maximize number of lifeboats. So it's a really simple function. We're just going to maximize the variable b. But before we do that, okay, so I guess I've already sort of assumed that I'm going to define my variable b to be the number of boats and then v to be number of vests, but obviously you can just keep x and y if that's comfortable. I like to use letters that correspond to the things that they mean when possible, just because then it's really easy for me to interpret my solution at the end, but ultimately it takes a couple extra seconds if you're using x and y. So as before, I've put in labels for boats and vests, and then I'm going to initialize them both to be 0. So in the cells where I want to store the value associated with boats and vests, I'm going to type in equals 0 for both. And then I like to highlight these, as you guys know, so I'm going to highlight them with the cursor and then choose bright yellow. Alright, so next thing, like I said, we have our objective function, and as I just mentioned, it's going to be b, and it's already formatted as red for me, surprisingly. And so now what I want to do is, in this cell, I want to reference the cell that holds the value of b. So I'm going to type in equals, and then b is held in A3, so I can either type in A3 and hit enter, or if I want, and this is often how I do it, I type in the equal sign and then I just click on the cell that contains the value that I want to reference, and it'll pop in A3 for me in that way. Alright, so that's my objective cell now, and just as a reminder, the ship's captain wants to maximize number of lifeboats. So I'm just going to type that in there. Alright, so now we're on to our constraints. And I always try to go ahead and do the implicit constraints, if there are any, just so I don't forget. And so for boats and vests, same thing holds as acres of corn and oats. We can't have negative values there. So I want to do b greater than or equal to 0, and here I'm just typing it in as text, so I don't have to put the equal sign first. And then same thing for v is going to be greater than or equal to 0. So we also had this constraint about, we have to have enough lifeboats and life vests for all of the passengers on board, and we were told that we can have up to 200 passengers. So we definitely have to have accommodations for 200 people. If we have less than that, it's a problem. If we have more than that, that's actually okay, right? So we know that each boat can hold 8 people. So I'm going to have 8b, and each vest has 1 person, so it's just 1 times v, which I'll write as v. That needs to be greater than or equal to 200, right? Because like I said, if we have more availability than 200, that's fine, but less is going to be a problem. And then the last constraint that we had deals with the amount of storage space required for the different types of life preservation things. And so each lifeboat takes up 6 cubic feet and each vest 1. So we're going to do 6b plus 1v. And let's see, we only have a total of 190 cubic feet for storage, so we definitely can't go over that, right? But if we're under it, that's actually good. Probably, because we can use that storage space for something else. So we're going to do 6b plus v less than or equal to 190. now that we have all of those typed in, we're going to tell Excel what we mean by those things. So give Excel the actual formulas that it'll use when we run Solver. So in column B, I'm going to handle all of the variables. So for B5, I want to reference whatever holds B. So I'm just going to click, we'll type equals and then click on A3. And as a reminder, I want that to be greater than or equal to the fixed value of 0. For B6, I first want to reference the cell that stores the number of vests, so that's B3. Again, greater than or equal to the fixed value of 0. For B7, I want to take care of 8 times the value of B plus 1 times the value of V. So that's 8 times A3 plus B3. That needs to be greater than or equal to the fixed value of 200. And then for this final one, I need 6 times the value of boats, which again, I'm going to click on A3 to get that. Add to it the number of vests, which is B3. This time it's less than or equal to the fixed value of 190, so I type in equals 190. And so now I think everything's accounted for, right? We've defined our variables, initialized them to 0. We have our objective function, which is just B, number of lifeboats. We know we want to maximize it. We have our 2 implicit constraints of non-negativity and our 2 explicit constraints, the first of which is just being able to save everyone's life, and the second one is having enough room to store the lifeboats and life vests. So we should be ready to run Solver. So since we already have that loaded in, we're going to go to our Data tab, click on Solver. And I actually still have everything stored in here, so I'm going to get rid of it so that we can do this all together. I'm going to delete. All right, pretend like you didn't see any of that. Okay, great. Okay, so for our objective, right now it's blank, so I'm going to click in this white space, and I can type in, remember if I want to use the dollar signs to fix it, which is a good idea, I'm going to type in the cell containing our objective value, which for us is B4. So I'm doing $B, $4. So that's how you would just type it in. We said we want to maximize it, so make sure that button's clicked. And then for changing variable cells, what I'm going to do this time is see this little icon to the right of the white box? If I click that, what I can do then is go and highlight the variable cells that I want. So to highlight more than one cell, I click hold and then I guess drag the cursor. So click, hold, drag to highlight the total number of cells. And then I hit enter and it takes me back to this box. Equivalently though, I could have typed in $A, $3, $B, $3 to give it that range that we want to see. Okay, next I have to enter all of my constraints. So I'm going to go to this add button and I get a new dialog box that pops up. So cell reference, the first one, let's see, I want to make sure that B5, this is my first constraint in black, this value, I'm just going to click on it to pop it in, needs to be greater than or equal to the value in cell D5. And if I'm done, like if that's all the constraints I have, I could click OK, but we have more, right? So I'm going to click Add, and then I can add a new one. So second constraint is for non-negativity of V. The cell I want it to reference is B6. I want it to be greater than or equal to the value in D6. Click Add. For the third one, I want to reference the number in B7. Make sure that one is greater than or equal to the value in D7. then last one, I want to make sure that this value in B8, so just click there to pop it into the box. This one is less than or equal to the value in D8. And then I'm done with my constraints, so I click OK. Alright, so remember that we can leave this box checked. We want to use the simplex LP or whatever says linear as our solving option. I usually take time to double check and make sure that these are all entered correctly, but I'm just going to be cavalier about it and go for it this time because I'm pretty sure they're good. So I'm going to click solve and wait for it. Kind of cool how you can see it, like I don't know if you noticed, but it was like changing the cells towards the end until it arrived at the final solution. So it tells us that solver did find a solution that satisfied all of the constraints. So it is the case, right, that an LP can not have an optimal solution, in which case solver will tell you that. You'll get some sort of message other than that it found a solution. So it'll usually say like there is no solution, or let's see, in the case where there, well, I'll leave it at that for now. So right, if there's no solution, it'll tell you that. So it's a good idea just to read this message before you actually look at the solution to be sure that you found something. So I'm going to click OK, and notice that it gives us the value of 31 2/3 for number of boats and 0 for vests. And that was almost surely, I think, the answer that you guys came up with yesterday. Oh, well, except you didn't have your objective function. So I'm pretty sure that that was one of the corner points, and it was the corner point that was largest in terms of the value b, and so obviously now that we know we're maximizing b, we're just going to choose that one, right? Because all of the other corner points b was, well, I think it was, what, like 0 for one of them and maybe 25 for the other, or something like that. So this is the optimal solution, which is great. And so, of course, this is the case where we wanted to ignore the fact that lifeboats and life vests have to take on integer values. But what if we did want our lifeboats and life vests to be integer values, which is surely the case, right? Because we can't, well, I guess 2/3 of a lifeboat is not going to be very useful to us because it won't inflate properly. Okay, so incorporating that condition in Excel is a lot easier than by hand. Although actually in this case, doing it by hand wasn't too bad, just because our objective function was pretty easy, and I don't know how much you all were able to think about that without knowing the objective function the other day. But so one option for considering the integer program problem is just to look at all of the lattice points within your feasible region. And so a lattice point is just where, you know, both variables take on an integer value. So if you're using gridded graph paper, it's basically at an intersection of the horizontal and vertical lines. So you could just test all of those points within your feasible region. Although if your feasible region is large, that might take a while. It's a little tedious, but that's sort of the obvious way to do it. There are more strategic ways, but we're not really going to talk about that much. But I did want you to think about that yesterday, which was part of why I included that other question at the end. But for now, we're going to do all of our integer programming in Excel. So it's going to be really easy to modify what we've already done in this example to make it an integer program. All I'm going to do is pull back the solver box. Everything stays the same, which makes it easy. I don't have to retype everything in. The only thing that's going to change is we're going to add some additional constraints. And so the first one is that I want the number of lifeboats that I have, which is this value right now, but it's always housed in A3. I want that to be an integer, so that's what int means, and then it tells you off to the side, oh yeah, you want this to be an integer. And then I also want that to be true of vests. And that's an integer. So now we have all of the same constraints, the same objective, but we've added the two conditions that number of boats and number of vests should be integers. Okay, so everything else is the same. I'm going to run solver one more time. And it's thinking. Okay, so solver came up with something. It says it found a solution. Cool. So we're going to click OK. And the solution it found is not far off from the linear program. So we're going to look at 31 boats, 0 vests. What's nice to do in this case is, well, and really in every case, it's kind of nice to check and make sure that your constraints actually are satisfied, because who knows, we could have made a typo or something. So it's telling you that the maximum value of b in this case is just 31, right? We already knew that. That is greater than or equal to 0. 0 is greater than or equal to 0. The total amount of passengers that we can accommodate is 248, which is great. It's even more than we can have capacity for, so even if a few people sneak on, we should be good. And then here we found out that we used a little bit less space than we even have, right? We have 4 cubic feet left over, which is interesting, right? Because I think this points to the possibility that you all may have been able to stumble upon yesterday, that for the integer program in this case, there's actually more than one optimal solution, right? Because we were just maximizing b, right? And 31 was the largest we can possibly get for b. But notice that if I added a life vest, so the first 3 constraints would still be satisfied. So this would bump up to 1, which is greater than or equal to 0. This would bump up to, I guess, 249, which is still greater than or equal to 200. This one would bump up to 187, which is still less than or equal to the total space that we have allotted for, right? So one other possible solution, it's still a feasible solution and it's still an optimal solution of this b equals 31, would be 31 and 1. Actually, let me just even hard code this in there so that we can see that change. Everything is still satisfied, right? So really we've got 2 optimal solutions so far. We can bump this up to 2. Notice that everything is still fine. We can even bump it up to 4. And that's as high as we can go, right? Because otherwise we're going to keep increasing the amount of space and we don't have any more. We sort of met all of our space requirements. So it turns out that there are 5 optimal solutions here. 1 for v equals 0, 1 for v equals 1, 2, 3, 4, so on and so forth. So that brings me to a point that I guess hinted at earlier, and then I was like, oh, I'm not going to tell you that yet, is that if there's more than one solution, Solver will not necessarily tell you that. So Solver will just pick one of the solutions that works and give that to you. So that's just something to keep in mind. It's not always clear to see that. Like I think here it was, right, because our objective function was so simple, but other times it might be a little bit trickier to see. So it's sort of good to get in the practice of kind of thinking about whether there might be other solutions. And when you're doing this by hand graphically, sometimes it can be easier to see that, right? Because if you're testing 2 different corner points and both of them give you the same optimal value, then that kind of indicates that really anything along that line segment between the 2 would also be a solution. So in that case, there are infinitely many. That doesn't pop up all that often, but it can, so that's a little heads up. Okay, so that's all for this example. In the next example, we're going to expand the problem a little bit, which should be fun. So I'll see you for that one.